Hello everyone, and welcome to our lesson on 14E, which is about differentiation from first principles. So the first thing, this is a discussion. It comes straight from your textbook on page 355, and it's just a review of what we've talked about with limits and tangents. So remember that if we have some general function that they've indicated here as y equals f of x, where we have a is a general point x and f of x, and b is another point, which is h units away from x along the x-axis, then we can calculate the secant. Okay, they call it the chord in your book. And we see that the secant line has a gradient or slope. Your book likes to use the term gradient of f of x plus h, that's y2, minus f of x, that's y1, over x plus h minus x, which is x2 minus x1. Okay, and we end up with this, which we call the difference quotient. Our last video talked about the difference quotient. Now, if we want to find the slope of the tangent at point A, what we want to do is shrink this distance between x and x plus h. We want to make h very small. So instead, we could plug in a bunch of different values for h that got smaller and smaller, as we did in class, 0.1, 0.01, 0.001, or we could just do what a limit says and apply the limit as h approaches 0, which means to imagine that h is going so small that it might as well be 0. When we do that, now we have a formula that helps us calculate the slope of the tangent at point A. Okay, and that turns out to actually be a function. If you'd like to review that in more detail, you can go to page 355. So far in Unit 1, or in our first couple of days, we saw limits of this form. Okay, we used a's instead of x's. Okay, and the a's were representing specific points that we wanted to calculate the slope of the tangent at. Okay, and that represents the slope of the tangent to the graph of y equals f of x at a particular point a and f at a, or what we call the instantaneous rate of change of y equals f of x with respect to x at x equals a. When we find the slope of a tangent, we're finding instantaneous rate of change. When we find the slope of a secant, we're finding the average rate of change. This limit plays a central role in calculus, so it's given a special name, the derivative. You might remember that from the videos we saw on the first day of school. Okay, but because this helps us calculate the slope of the tangent, we gave it its own name and we give it its own notation, f prime of x. This little apostrophe here looks like an apostrophe, but it's read as f prime. Okay, so therefore we can now say that this equation that we called the difference quotient is actually the derivative, and it has its own notation. And when you use this limit to determine the derivative of f of x, we call it determining the derivative from first principles. So if I ever ask you to find the derivative from first principles, we must use this formula to calculate it, even if we know other ways. Okay, so a little bit of practice here. If we've got this function f of x equals the root of x plus 2, and we need to find f prime of x from first principles, they didn't give us a point this time. So we're going to follow similar procedure that we did before when we were trying to find the slope of the tangent, but we're going to keep x general, okay, which means a little bit more algebraic manipulation. So I'm going to plug in. I know that the formula for the derivative from first principles is the limit as h approaches 0 of f of x plus h minus f of x all over h. And what I'm going to do is I'm going to plug in x plus h into this expression up here for x, and then I'm going to plug in x up here for x. Okay, and I notice that I get this expression with some radicals. So I'm going to rationalize the numerator and multiply by the conjugate. Okay, remember to just keep the same radicals, change the sign in the middle to the opposite. When I expand that numerator, I end up getting x plus h plus 2. I multiply these two, and the square root cancels out. I multiply the outside terms and the inside terms, and those two terms cancel each other out. And then I multiply my last terms, and I get x plus 2, okay, because these radicals also cancel out. In the denominator, I have what looks like a huge mess, but it's going to be okay, because eventually some of the h's are going to turn into zeros. Once I expand and simplify here, I end up with x plus h plus 2 minus x minus 2. Remember that this minus sign applies to both terms in the bracket. and I can cancel out the x's and cancel out the 2's, leaving me with just an h in the numerator.